on. Sorry, I was a tad late today, so let us see. Okay, so far we introduced particle kinematics. So we introduced position, velocity, and acceleration vectors. We talked about rectilinear motion, and we talked about kind of motion expressed in the Cartesian basis. So today we're introducing a new basis for space. That's called the cylindrical polar coordinate system. We're going to start by introducing the planar version of it, and then we're going to extend it to space. So our plan for today is to do the cylindrical polar coordinate system. We're going to start with the polar, which is the space version. Then we'll introduce the cylindrical, which is the 3D version. And I also want to talk about constraint systems like pulleys, and whenever you have particle in two slots, just system subject to constraints. So let us start with polar coordinates. We're still dealing with a particle, but for now it's moving in the plane. So the polar coordinates is the planar coordinate system. The cylindrical polar is the 3D extension. Polar coordinates. So this is our particle tracing a typical 2D curve. So our particle P. And I can draw my position vector from the origin to the particle. I'll call it R. So R is the position vector from the point to the particle. I'm going to introduce, so this position vector, I can write it in the Cartesian basis as xex plus ey. Right? Now, I want to introduce new coordinates, r and theta. Define r. R is the square root of x squared plus y squared. And notice that r is always positive, right? What physical quantity does r represent? Yes?
The distance from the origin.
The distance from the origin to the particle, right? Which is also what? Yeah. What is it? It's the magnitude of the r, right? It's the magnitude of the position vector r. So r is the magnitude. Sorry. R scalar is the magnitude of the position vector r. It's always positive. It's the distance between the particle and the origin. So it's the magnitude of the position vector. We will also define an angle theta such that tangent theta is equal to y over x. Okay? So again, we're looking at a particle moving in the plane. We're introducing a new basis, the polar coordinates for planar motion. A particle moving in the plane has position vector r is equal to xex plus yey. I'm introducing two new scalar coordinates, r and theta. R is the square root of x squared plus y squared, and tangent theta is y over x. And r is the magnitude of the position vector r of the particle. You see the difference between vectors and scalars? They're distinct, they're different, right? R vector is the position vector, R scalar is its magnitude. What about theta? What does theta physically represent? So if our scalar is this length. That's our scalar. What does theta represent? Which angle do I have whose tangent is y over x? Yes. The angle between which two lines? No, the angle between EY and EX is 90 degrees. It's a right angle. Yes? The angle between EX and R, right. So this angle here is equal to theta. Why? Because if I draw my position vector R, I'll draw it on the side, EX, EY. What is this distance? Here. It's x, right? Because R is x, EX plus y, EY. And this distance here is y. This distance is y, this distance is x. This is a right triangle whose sides are basically x, y. So the tangent of this angle is y over x. So that's the angle theta. Does that make sense? Take a minute, make sure your neighbor understands this well. So that's the angle theta. Any questions? So raise your hand if your neighbor understands this. Okay, cool. So I'm going to introduce a new basis now. That's the cylindrical polar. Well, that's just the polar basis, actually, not cylindrical yet. But I'm going to introduce a unit vector ER and a unit vector E theta that's perpendicular to it. So notice ER is in the same direction as the position vector R. And ER dot E theta is equal to 0. And this is an orthonormal basis. So ER and E theta are both unit vectors. So ER is along the position vector R and E theta is perpendicular to it. Notice that if I draw ER, some vector ER, I can draw two perpendiculars to it, right? Two unit vectors that are perpendicular to it. I can draw E theta up or E theta pointing down. Which one do you think I will choose here? The E theta pointing up or the E theta pointing down? Up. Why? Any ideas? I haven't told you this yet, but I want to see if you would guess it. Yes?
Because of the right-hand rule, like you want the thing pointing up?
Exactly. So I want ER cross E theta to be always the same as EX cross EY. So I always want that ER cross E theta to be equal to EX cross EY. So here, if I have my Cartesian basis like this, EX cross EY is outside the page. I also want ER cross E theta to be outside the page. So this is how E theta is uniquely defined. Okay? Some might say that E theta points in the direction of increasing theta, which theta increases from EX to ER. Okay, you also see this statement around. Okay, so then ER, E theta is a rotation of EX, EY by an angle theta. By an angle theta, and theta is positive if I'm rotating in the direction of ER, EX cross EY. So this is my situation here. Ex, Ey, and Ex, Ey, Er, E theta. So do we see that Er is theta is a rotation of Ex, Ey by an angle theta? Positive like this in the direction of Ex, Ey. So that indicates the direction of the positive rotation. Any questions so far? So now, questions? Okay, so now if I want to express Er, the components of these two vectors, Er, E theta, along Ex and Ey, so that I have something like Er is something Ex plus something, some term Ey. E theta is some term Ex plus some term Ey. What do you think these missing terms should be? Take a minute, work on it. What do you think these missing terms should be? Okay, so what do we think? What is the first term? Sine, cosine? Cosine theta? Raise your hand if you agree. Okay, so that's cosine theta. Ex plus what? Sine theta Ey. Right, so this here is a right angle. What is the length of this side of the triangle? The magnitude of Er is what? 1, right? So this is a right triangle, length 1, angle theta. So this Ex component is going to be 1 cosine theta along Ex, and the Ay component is going to be 1 sine theta. And notice this is a unit vector. So if I calculate the magnitude of Er now, it's going to be equal to 1. What about E theta? What is the component here? Negative sine theta. Notice this component, magnitude sine theta, but points along negative Ex. Minus sine theta Ex plus cosine theta Ey. Okay. Any questions about this? So these vector projections should have been our bread and butter in statics. If you have any questions about this, let me know in office hours. Okay. So this is Er. These are the vectors. Unit vectors Er and E theta expressed in the Cartesian basis. Very well. Okay, so now remember when we introduced the kinematics of a particle, we introduced the position, the velocity, and the acceleration vectors, and we wrote these in terms of, well, in the Cartesian coordinates. R is x axis y ey plus ez, v is x dot ex plus y dot ey plus z dot ec, a is x double dot ex plus y double dot ey plus z double dot ez. I want to do the same thing in this polar basis. So how can I write my position vector in the polar basis? Not in terms of x and y, but in terms of r and theta. So this vector r, how can I write it in terms of the polar basis? What do we think? What is its magnitude? R scalar. What is its direction? Unit direction, small er. So how can I write it? R, small er. Okay. So this is how I write my position vector in the polar basis. R is RER. Now I want to calculate the velocity and acceleration vector, so I will need to take the derivatives of ER and E theta. So let us do that, and then we'll calculate V and A. Okay. So I have that ER cosine theta x plus sine theta EY. How do I calculate ER dot? I take the derivative, but I want to take a derivative with respect to what? Well, I want an ER dot. So that's the derivative with respect to what? Time, right? So theta is itself a function of time, right? As the particle moves, r and theta, they change. So r is a function of time, theta is a function of time. So then how do I take this derivative? What's the derivative of cosine theta with respect to time? What is it? Negative sine theta, just that?
Times like theta dot.
Exactly, which is using the chain rule, right? So dER, I can write this as dER by d theta by dt. That's using the chain rule. So that's going to be theta dot, and the derivative of this with respect to E theta minus sine theta. Ex is fixed plus cosine theta Ey is fixed, right? So then, what is this vector here? We have a name for it. E theta. Okay. Okay, so since I feel a little bit sleepy this morning, we're going to have a short quiz to start our day. So the answer is there. Yes. Let's take 10 minutes to do this. You're welcome. Yes. Any extra papers? Anyone still needs a paper? Okay, so this is 2 pages, but for now we can start with the first one. Thank you. Okay, so go ahead, start with the first. Oops. What is it? Yeah. Oh. Gosh. Sorry. No looking at online resources, you should be doing this yourself, okay? Yourselves. If I see someone's looking somewhere online, then I'll have to make electronics free quizzes. What is it? No, don't look at the notes. You need to derive this yourselves, and if you have any questions, let me know. Any questions? So you need to take the derivative of this, right?
Yeah.
Yeah, V's are the had my mic off for like 10 minutes. It's fine. Okay. Right. So I have these expressions. ER dot is equal to theta dot E theta. Okay, how did we obtain these expressions? We started with ER and E theta, what they're defined to be in terms of EX and EY, and we took the derivatives. We did this, we found these relationships analytically by doing derivations. Now, in some textbooks, they don't do that. They find these equations geometrically. Let me show you how a little bit. So they say that I have kind of ER of T, E theta of T, and then I have ER and E theta of T plus delta T. So I have my delta theta here. And you can see that the delta ER I have a better drawing in the notes, but delta ER points almost along E theta, right? Delta ER almost points along E theta. And delta E theta almost points along minus ER. So what they do is they use geometry plus when delta T is very small, differential time, differential theta, ER dot is going to be along ER dot is going to be along E theta, and E theta dot is going to be along minus ER. That's for the directions, and then for the magnitudes, they use kind of like triangles and geometry to obtain these expressions. So I just wanted you to be able to kind of introduce you to this in case you see it in some textbook. Okay, questions? Okay. Let's try to give an intuitive meaning, or just try to give an intuitive meaning for the components of the acceleration. We're going to try to do this here, and then we're going to go through this again when we go through rigid bodies. Okay? So, okay. Any questions so far? So we've introduced the polar basis, the polar coordinates, the basis vectors, and the position, velocity, and acceleration vectors in the spaces. For that, we needed to take the derivatives of ER and E theta, the polar bases. Okay? Now the acceleration, it has 4 terms, and they have names. Let's look at the radial component of the acceleration. Where does this term come from? Can you think of some motion where the acceleration is purely radial? So A is just R double dot ER. Is that possible? Yeah. So if the acceleration is purely radial, what other restrictions do I have on the motion? It's linear, right? Because what should theta dot and theta double dot be? 0, right? In this case, theta dot is equal to 0, theta double dot is equal to 0. What does this mean? That the angle theta is constant, right? Okay, and if a particle is moving on a curve such that the angle theta is constant, then how is the particle moving? So you see, if I have a curve and the particle is moving on the curve, but as the particle moves, the angle theta is constant, then how is the particle moving? Just on a straight line, right? R could be changing, but theta is fixed. So that this motion is rectilinear, right? We need board space. Okay. So then the motion is rectilinear. Okay? As an example, for example, your friend gave mentioned the linear spring. So if I have a system like this, and if I take my origin to be here, and this is the position vector of the particle, this is ER, then notice that if the spring is oscillating up and down, the motion is rectilinear purely along ER. Okay? So in this case, the spring would be supplying the radial acceleration, and that's the only component of the acceleration that's there, right? If the particle is moving on a straight line, constant speed, then what is its acceleration going to be? 0, right? And notice here that this intuition is not foolproof, because what I can do is that if I offset the origin here, let me choose a different color. If I offset the origin a little bit, okay, even though the motion remains the same, how do I draw my polar basis? Well, first I have to draw my position vector, and dr is going to be like this. Then is the acceleration of this particle now, will it remain purely radial if I shift the origin? No. So this intuition that we're trying to give here is not foolproof. And the thing with the polar coordinates is that the description of the motion depends a lot on where I pick my origin to be. Sometimes it's obvious when I'm moving on a circle, I'll pick the origin to be at the center of the circle, and other times it's not. Okay? So here, not purely radial. Okay, I will erase the bottom board here. I want to keep the drawing up there. Okay. Now, let us do this centripetal component. Can you think of a case where the acceleration is purely centripetal? Is that possible? So can you think of a case? Let's just. Is this possible? Yes. It's, how did you know? It is possible for a particle that's just tracing a circle with a constant speed. How did you know? So for the acceleration to be purely centripetal, what other components of the acceleration should be 0? Yes, exactly. Everything else should be 0, right? So r double dot should be 0. R theta double dot should be 0. 2 r dot theta dot should be equal to 0. So what does that mean? Yeah. So for this motion to be possible, all of these need to be equal to 0. So from here, I'll get that r dot is constant. From here, I'll get that theta dot is constant. From here, should be equal to 0. So I either will need r dot to be 0 or theta dot to be 0. But if I pick theta dot to be 0, then I'll get the acceleration is 0, and then I've done nothing. So theta dot needs to be different than 0. So r dot needs to be 0. So r needs to be constant. And when r is constant, what does this mean? Then I'm tracing a circle, right? So the situation is like this. This is my origin. I have a particle that's tracing a circle. I can draw the position vector and the polar basis. Okay? So if you're tracing a circle, if a particle is tracing a circle such that the radius of the circle is constant, but also such that theta double dot is 0, theta dot is constant, at a constant angular rate theta dot, then the acceleration is going to be purely centripetal. Okay? Let me go and check what the velocity of the particle is. V is r dot er plus r theta dot e theta. Right? In this case, r dot is what? R dot is what? 0, right? So V is r theta dot e theta. And notice that the magnitude of V is equal to the magnitude of r theta dot, which r is constant, theta dot is constant. That's constant. So even though the speed is constant, the acceleration is not constant. How do we explain this? Even though the speed is constant, the acceleration is not constant. How do we explain this? Even though the speed is constant, the acceleration vector is not. Why? What's changing direction? The velocity vector, exactly. So the acceleration vector does not only depend on the speed, which is the magnitude of the velocity, it depends on the velocity vector. So it's affected not only by the change of the magnitude of the velocity vector, change in speed, but also it depends on the change in direction of the velocity. So here when you're going on a circle, the velocity vector is changing direction. So even though your magnitude speed is not changing, its direction is always changing. The vector direction is always changing. So the centripetal acceleration is due to that. It's due to the change direction of the velocity vector. So the radial acceleration is due to the change in the rate of change of r, the distance from the origin. Centripetal is due to the change in the angle theta. We can jump to the tangential acceleration. Can you think of a case where the acceleration is purely tangential? Is this possible? Chat with your neighbor, let me know what they think. Is this possible? So what do we think? If you don't have a neighbor, you can move and find a neighbor. We're going to need a neighbor in this class. So raise your hand if you think yes, we can find a motion whose acceleration is purely tangential. Raise your hand for yes. Raise your hand for no. Raise your hand for yes. No. Okay. Why do you say no? So the majority says no. Why? So what would that motion entail? If relaxation is purely tangential, then all the other components are what? 0, right? So r double dot would be 0. R theta dot squared would be 0. And 2r dot theta dot would be 0. So we cannot have r to be 0. That should be sticking at the origin, right? So from this, you'll get that theta dot needs to be equal to 0. But if theta dot is equal to 0, then theta double dot cannot be non-zero. This is constantly equal to 0. So that's not possible. It's not possible. It's not possible to have a motion whose component is just, or whose acceleration is just tangential. At least what you're going to have, if theta dot is changing, at least what you're going to have is you're going to have the centripetal component of the acceleration. So the minimum case is that I have a particle that's moving on a circle, but now it's not moving at a constant theta dot, it's moving at an accelerating theta double dot, non-zero. In this case, the component of the acceleration is going to be centripetal and tangential. We cannot have tangential on its own. So where does the tangential component of the acceleration come from? Based on this, where does the tangential component of the acceleration come from? Yes?
Like changing speed.
Yeah, kind of. Changing, rate of change of the angle theta dot. The rate of change of theta. So which has to do with the changes of speed. Okay? And then finally, any questions so far? So this information is not clear cut. It's just giving you a rough intuition of what these components mean, where they come from. Okay? The centripetal component of the acceleration, it's a little bit more complicated. It has to do with two things. Okay. Sorry, Coriolis. A is equal to 2r dot theta. Okay. Okay. So this motion, there is no motion where the acceleration of the particle is just only has a Coriolis component. Whenever you have a Coriolis component, then r dot is not 0, so you have that, and the dot is not 0, so you have the minus r to the dot squared term at least. So at minimum, you have this. And this component, the Coriolis component of the acceleration, has two terms. It's due to the change in the distance from the origin, due to the change in r dot, and due to the change in theta dot, meaning that the frame is rotating. So the centripetal component of the acceleration is related to two things: r dot, the rate at which the particle is moving away from the origin, and theta dot, the rate at which the particle is moving. So you might hear that whenever you have a particle in a rotating frame, then it has a centripetal force, a Coriolis force. I don't like the term, it's an acceleration component. For now, you know a little bit what it is, but we're going to talk more about it when we go to rigid bodies, okay? So we'll circle back to this when we talk about rigid bodies. Okay, questions? Yes?
Is that the theta dot equal 0 or theta equal 0 at the very right bottom?
Theta dot is equal to 0. Yeah. Okay. So whenever we do particle kinematics, the goal is to be able to find the equations of motion of a particle, describe the motion of a system. So we're going to move directly from kinematics and polar coordinates to kinetics, forces. So let's take an example, which is the simple pendulum. So let's consider the simple pendulum. Oops. Okay. So the simple pendulum, we want to find this equation of motion or equations of motion. Well, actually, that's a good question. How many equations or equations of motion are we gonna find for the simple pendulum? How many equations do we need to describe its motion? Remember equations of motion, differential equations of motion? How do we know how many equations we need? It's based on what? Exactly, degrees of freedom of the system. How many degrees of freedom does the system have? So it's a particle moving in the plane, oscillating in the plane, but it's also subject to the constraint that the distance between the particle and the origin is constant, right? It's equal to the length L of the string. So then how many degrees of freedom does the system have? How many? 1, right? The angle theta, if I know theta, then I know theta is a function of time, then I know how the system is moving, right? So this system has 1 degree of freedom, 1 constraint. 1 DOF, which is the angle theta, and I have the constraints that it's planar, the motion is planar, and also that the length of the rod is fixed. Okay, so I can express the position vector of the particle in Cartesians. And I can express the position vector, and they're equal. The same vector I can express in multiple bases with the vector remaining equal as RER. Okay? Now, in which basis can I express the constraint of the length of the string being constant more easily? So the length of the string is constant, meaning that the position vector has constant magnitude, right? In which basis can I express this constraint more easily? The polar basis, right? So in the Cartesians, this constraint becomes the square root of x squared plus y squared is equal to L. But in polars, this becomes that R is equal to L. So this is kind of giving us an intuition of when it's easier to use one basis versus the other. It's never wrong to use one basis versus the other. There's no right and wrong, but it's more of a what basis is more conducive to a quicker, more elegant, cleaner solution. And with time, we learn this intuition. Okay? Polars is easier here for this problem. So go ahead, take 1 minute. I want you to draw the polar basis here. So draw ER and E theta on the figure. And R and theta. So draw the polar basis, ER and E theta, and the lengths or the scalars r and theta, length and angle. If you're done, then you can draw the free body diagram and move on to the next steps. So polar basis, that's very, very important. One of the core concepts you need to know. You cannot pass dynamics if you don't know how to draw the polar basis. Yes?
Sorry, I think it's earlier, so we did this at the end.
Not yet, yes. Yeah. So where is your polar basis? Okay, good job. A polar basis, where is it? This is that comes up. But why? But it doesn't have to do with that. It has to do with the ex cross ey and er cross e theta need to have the same. Yeah. Crush product. Okay. So I think most of you have got it. I draw my position vector r from the origin to the particle. ER is along r for polar, so this is a planar problem, so ER is along r. And how do I draw a theta? Perpendicular to it, up or down? Y up? Yes, ER cross E theta is the same as EX cross EY. So that's my polar basis, and this is my angle theta. This is my distance r. Okay, so I want to follow the 4 steps to solve this problem to find the equation of motion. Remember, step 1 was choosing your system, which is the particle, setting up the bases, writing the expression for the position, velocity, and acceleration vectors. So here I'm going to start with r is LER, and remember that L is constant. So what are its derivatives of L? What is L dot and L double dot? 0, because L remains constant throughout the motion. So V is L theta dot E theta. So I'm taking the derivatives. L minus theta dot squared ER plus theta. Okay, so this is step 1. And the system is going to be M. I promise I'm usually neater, but I'm running out of board space today. Okay, M. What is step 2? Free body diagram, exactly. What are the forces acting on the particle? Exactly, tension and the weight. Tension, what is the direction of the tension force? Yes, along the string, and the string is always going to be in tension, so that's T like this, weight like this, right? So what is the direction of T? Yes. And the weight is along EX. So here the spring is always in tension, so this T is always positive. Okay? So this is my free body diagram. I have 2 forces acting on the system. So because I have this constraint that the length of the distance from O to P is constant, the length of the chord is constant. Whenever I have a constraint, then I have a constraint force. So the tension is actually a constraint force. It enforces the fact that the particle remains always at the fixed distance from O. Do we see that? Okay. Step 3. What is step 3? What was step 3? I write the vector equation of the balance law, the balance of linear momentum here. the vector equation of the balance of linear momentum F equals ma. So I'll copy all the forces from the free body diagram minus TER is equal to m Step 4, I'll project and analyze. Any questions so far? Okay. Yes.
Would it be all right to go with the free body diagram, going straight to kind of breaking weight into components?
Breaking weight into two components?
Into like along the bases.
Yes, but you don't need to. I have no problem in one equation using multiple bases. You see, like in this equation, I have the polars and I have the Cartesians, and that's fine. Yeah, you can break it up. You don't have to. Was there a question? Yes.
I was going to ask, MGEX is positive, EX is also going down?
Exactly. You see, the weight and the x, they have the same direction. So here I flipped the typical EX, EY, I flipped them. Yeah? Yes?
Did you choose EX to go down because you wanted to create the theta with R?
Yes. Why did I choose EX to point down? Any guesses? Yes?
So that the ER equals the cosine theta EX plus the sine theta EY.
Great point. That's always going to be the case. So these relationships we found, they will always be true as long as EX, EY, and ER, E theta are rotated by each other by an angle theta along their cross product. So that's always going to be the true. Yes. Any other? Yes.
Is it because like when the string is hanging straight downward, then when it moves, it's moving like up towards EY?
Right. So when the string is hanging vertically downwards, what is theta? 0. That's why. And then when you're swinging, in this case, theta is negative and then positive, right? But if I were to take EX and EY pointing up, EX and EY pointing down up, and the string is over here, then this is ER, and E theta is in which direction? Like this? No, like that, right? EX, EY. E theta. In this case, when the string is hanging vertically down, then the angle theta is minus pi by 2. So you're oscillating about the minus pi by 2 instead of oscillating about 0. So that's kind of why I chose EX, EY to be like that. Okay. Okay. All great questions. Any other questions? Okay. So you see this vector equation here, the balance of linear momentum, it has components along ER and EX. So this is a vector equation in the plane. How many scalar equations can I get from it? How many independent scalar equations can I obtain from this vector equation? 2, right? By projecting it along 2 directions in the plane, 2 independent directions in the plane. So here, the tension force T is an unknown. This here is an unknown. And the differential equation of motion is an unknown. Theta as a function of T, it's an unknown. So I can obtain two informations from this equation, the differential equation of motion and an expression for the tension force T. So looking at this equation, I can project it along a number of directions, EX, EY, ER, E theta, and we're gonna do those for practice. But there's one vector in which I can project this equation along, and I'll directly obtain the equation of motion without involving the unknown tension force T. So again, there's one unit direction I can project this equation about, and I'll just get the differential equation of motion without involving the unknown tension T. What is that direction? What do we think?
theta.
Your friend is saying E theta. E theta. Why would that be? If I project this equation along E theta, what will happen? What is the projection of the tension force along E theta? 0, because it's along ER. So I get rid of the tension force. If I project along E theta, I'll get this term to be 0. I'll get mg Ex dot E theta is equal to mL theta double dot. What is Ex dot E theta? I erased the expression, but Ex dot E theta, well, we have E theta is cosine theta Ex plus sine theta Ey. So what is Ex dot E theta? Cosine theta, right? Ex dot E theta is cosine theta. So I can take E theta dot Ex dot Ex dot Ex. This term is going to be 1, 0. So I'll get cosine theta. So this equation becomes m go away. There's a negative cosine theta. Why? There's a minus sign missing, but where does it come from? Oh, this is ER. You're right. Sorry, this is ER. E theta is minus sine theta Ex plus cosine theta Ey. So this will be minus sine theta here. E theta dot Ex is minus sine theta, right? So I'll get cancel out. Theta double dot plus G over L sine theta is equal to 0. So technically I know the problem constants G and L, and if I know the initial conditions for this motion, I can solve for theta as a function of time. Now I cannot solve this differential equation by hand. I'll have to involve things called elliptic integrals. But you can solve it numerically pretty easily, and that's what you're going to do in your homework. You're going to solve a version of this equation in your homework. Homework 2 due this week. Okay, so this is the differential equation of motion. Given initial conditions, given the problem constants G and L, I can solve for theta as a function of time. Right? Do we see that? And do we see how by projecting along E theta, we directly got rid of the tension force and formed the equation of motion. Now, if I want to go back and calculate the tension force in the spring, what do I do? If I want to go back and calculate the tension force in the spring, what do I do? Yes?
Do you project along ER?
Yes, I can project along ER. If I project along ER, I'll get minus T plus mg Ex dot ER is equal to minus mL theta dot squared ER dot ER, which is 1. What is Ex dot ER? That's cosine theta. So I'll get T is equal to mg g cosine theta plus m plus L theta dot squared. Okay, and this is my tension force as a function of time, and it's going to vary with time. The tension force is not going to be constant throughout the motion of the spring, right? It varies with time. Once I know theta as a function of time, I can calculate the tension force pretty easily. You're going to do that in your homework, I think, if I remember correctly. In your homework, you're going to look at the pendulum, but it's not going to be, it's going to be a spring pendulum. Instead of a cord of fixed length, you're going to have a spring of some stiffness. Okay? So, differential equation of motion T. Now, just for practice, project this balance law along Ex. Just for practice, let's project this balance law along Ex. What do I get if I project this along Ex? What's the first term? Minus T, what is ER dot Ex? Cosine theta. The second term I'll get what? Mg is equal to what? What is ER dot Ex? Cosine theta, so I'll get M minus L theta dot squared cosine theta. What is E theta dot Ex? Negative sine theta. Okay, so that's just for practice. But you can see that I could have projected along Ex and Ey and then eliminated T. I would have gotten the same thing as this. Have we seen this differential equation of motion before? Raise your hand if you have. Yeah? In what context have we seen this? For a spring? Okay. Sometimes you see this equation, but they simplify it, right? What do they use to simplify it? Yeah, well, this term here they call omega n, the natural frequency of the system, omega n squared. Okay. But there's a simplification that typically is made here to be able to integrate this by hand. Yeah, the small angle approximation. That sine theta is almost equal to theta for small angles. So if you're oscillating at small angles, sine theta is almost equal to theta. So they get rid of the sine, and then you can integrate this equation by hand. It becomes basically sines and cosines. Okay, which is the same equation as the spring simple harmonic oscillator. It's the same equation of motion once you get rid of the sine term. Okay. Great. Shall we take like a 5-minute break and then reconvene? Let's do a break, just 5